Factoring. We love factoring. We can factor a polynomial that has a common factor. That means every term has something common in it. Trinomial squares, we're going to talk about what those are again. We're going to talk more about differences of squares. We've talked about these before. We're really going to focus on them today. And this very powerful way of factoring by grouping. A little review now of multiplying polynomials. Here we have two binomials. When we have binomials, we might want to use the first outside, inside, last method to make sure that we multiply every term by every other term. So we multiply these two together. That's our first. And that's our outside. And then we do our inside and our last. And what do we do with these after we've multiplied them? We add them all together. So we get x squared for our first, and then a plus, see we're adding, and then we get plus 2x plus 6. We combine like terms, and we have our simplified answer in the form of a polynomial. How about this one? Same approach. The first, that's right, we multiply the 2 times the 2 as well as the x times the x. Then the outside, the inside, and the last. Combine like terms. Oh, they cancel each other out. Indeed. So we end up with 4x squared minus 1. Now you probably recognize this as difference of squares. And that's exactly what it is. We took, this is a shortcut you can use for any time you have conjugates. Square the first term, square the last term, the second term, and then put a minus sign beside them for difference of squares. This only works when you have conjugates. And you will remember, we've talked about it I think quite a bit, that conjugates are when you have the same first terms and the same second terms. One of them is a sum, the other is a difference. Conjugates. Multiply together conjugates and you get difference of squares. Write this as a product of prime factors. What's a prime factor? Something which is not evenly divisible by anything other than 1. Well, I think 5 could go into this, so let me see. This would become 5 times what? Okay, 21. I heard you. And 21, can we factor that? So we've got 5 times 3 times 7. So there it is, written as the product of prime factors. We're ready to move on. Whoops, not that quickly though. Here are terms that have common factors. We are going to see what do we have in common with both of these factors. Do you see anything? Certainly not an x, because this doesn't have an x in it. I'm listening and I'm hearing. So we're going to factor a 3 out of this. Basically, when you say factor, you're saying you're going to divide by that. So we're dividing this by a 3 and then pulling it off to the side. That's what we do in factoring. When we divide this by 3, now do we have any common factors between these two? No, we don't. How about this one? This one is interesting because indeed this time we have y in both of these. So we're certainly going to be able to factor out y. In fact, we can factor y out twice. We can factor out y squared. What else can be factored out of here? If we look at the numbers, certainly that's right, a 7. Up here I have a little reminder for you. Remember the identity property of multiplication. What was the identity property of multiplication? That anything retains its identity. Let me just pick a number, 13. 13 retains its identity when it is multiplied by 1. Right? It's still 13. And while we're talking about identity properties, just for the fun of it, what is the identity property of addition? What is it we can add to 13 that will not change 13's identity? Indeed, right. The addition identity is 0. The multiplication identity is 1. Very good. All right, so back to this one. When I divide 7 by the 7 I'm taking out of it, I have 1. Indeed. When I divide y cubed by y squared, I am left with y. And when I divide this by y squared by y squared, I get 1. And I divide 14 by 7. Now that looks very messy. I'm sorry about that. The way I should write this is 7y squared y plus 2, right? That would be the simplest way to write that out. How about this one? This one looks interesting. First I'll look at our numbers. Is there anything I can factor out between 6 and 21? Well, indeed there is, a 3, right? And they both have u's. How many u's can I factor out? Let's see. I can factor u out once and only once because it only occurs once there. How about v? I can factor v out as a squared term. So that's my common factors. Now, what's left? When I divide 6 by 3, I'm left with 2. U squared by u, I'm left with u. And v cubed by v squared, I'm left with v. Then, plus my second term, 7. U divided by u is a 1. V squared divided by v squared is 1. So there it is. How about this? 3 terms to look at, and they all are divisible by 3, so we'll factor that out. They are all divisible by x squared. They are all divisible by y squared. When I say divisible, I mean evenly divisible, of course. Now I'm going to divide the first term by 3x squared y squared, leaving me with 3x. And I will divide the second term by 3x squared y squared, leaving me with 2 times 1 y. Now the third term divided by 3x squared y squared leaves me with, thank you, yes, that's right. Now everything we did here had a common factor, so you might come to your mind that all polynomials have common factors. They do not. We have examples here that all had a common factor, but very often there is no common factor. Factoring trinomial squares. I love these, and we are going to see them later on in the course, so we should get really familiar with them. Let's start with this one. This looks very interesting because we have a perfect square as our first term and a perfect square as our second term. This actually is a pattern that we should become familiar with. If I look at this pattern over here, a squared plus 2ab plus b squared, and try to relate it to this, I would have to say that a is my x, and b is 4. Well, let's see if that makes sense. A squared, x squared, plus 2ab, whoops. Okay, so I'll go to this one. A squared minus 2ab. Let's see if that one works. Minus 2 times, we'll do the b, that would give me the negative 8 times x. So that one works there. And then finally plus b squared, which is 16. Notice that any time you have a trinomial square, this third term, the b squared, is positive, and of course the first term is positive. These are, we don't bother writing that, but you know that's true, right? Okay. So we have this one now. What can we do with this? Now because we've got a negative here, it doesn't fit this pattern. It is not a perfect square trinomial. Okay? Here's how you can test to see if you've got a perfect square trinomial. First of all, do you have two terms which are squares? Well, you don't. You don't. Because if this had been a negative 4, it would square up to be a positive. It would square up to be a positive 16. Well, are the two squares, are two terms square? No. Are the square terms positive? No. Does double the product of the square roots, whew, so the product of the square roots, x times 4, equal the middle term? Factor if possible. Ooh, this one looks good. This is a difference of squares. What did we say was the pattern that gives us a difference of squares. That's right, isn't it? So we take the square root of this, x, the square root of this, 5, make one a sum and the other a difference, and you are done. Here's the pattern. Memorize. Try this one. Is this a perfect square? You bet. I'm going to make a little more room between my parentheses here because we've got more numbers to deal with. 3x times 3x would give me 9x squared. 4y times 4y would give me 16y squared. So we've got a sum and a difference. We multiply those together, we get a difference of squares. How about this one? So interesting. Huh. Do I have... Is it possible that I've got differences of squares here? You know, it is. If I rearrange this, you may see what I see. Whoops. I'm going to change colors. And I'm going to look at this as my first term. Do you notice anything about this? Does it resemble this in any way? Pretty tricky, isn't it? If you multiply x plus 1 times x plus 1, you get this perfect square trinomial. So, in fact, we do have a difference of squares. And when we go to factor that, what did we say we do? We divide it into conjugates. We take the square root of the first term, which is x plus 1, and then we take the square root of the last term. We make one a sum and the other a difference. And we factored using difference of squares. You can tell now that you are in Algebra 2. Because you did something similar in Algebra 1, but you probably didn't do this. Here we have, nested within a difference of squares, a perfect square trinomial. So, is it necessary that there are only two terms? We have seen that it is not necessary. We may have a difference of squares with 4 terms. Are 2 terms squares? Yes. Now, I am stretching things a little bit because I'm referring to this inside parentheses as a term. And it is, in fact, a term which consists of a binomial. We do have to look to see whether or not the squares have opposite signs. So in this case we had, this was a plus and this was a minus, this was a plus and this was a minus. In this case this was a plus and that was a minus. Factoring by grouping, I love this technique. It allows you to solve any of these problems. So we're going to try factoring this if we can by grouping. Now when you have 4 terms, now you're probably wondering, why don't I just combine these? because you see right away that we've got like terms. I'm going to be showing you here how you do factoring by grouping, and it is always done in this way. You take the coefficient of your first term, which in this case was 1, your coefficient, or your, in this case it is the number itself, 6. You multiply them together and you've got 6. And then you look for factors of 6 that when you add them together, will give you a 5. So that's a 3 and the 2, and that's what you see right here. This allows us to do grouping. We take the first binomial, or first two terms, and consider it like a binomial, and then we look, is there anything we can factor out of here? Is there anything common in here? Well, certainly there is, an x. So we factor that x out, and when we do, we're left with x plus 3. Then we've got plus this. Is there anything common here? Indeed, 2. And when we divide everything there by 2, we get x plus 2. Interesting. Oh, what am I saying? It's x plus 3. Thank you. I heard you. Maybe the rest of you didn't hear her, but somebody told me. I made a mistake there. X plus 3 here, x plus 3 here. In this term and in this term, I have a common factor. It is a binomial, and it is x plus 3. I'm going to factor x plus 3 out of this term and this term. And when I do, when I divide this by x plus 3, I'm left with x. And then I divide this by x plus 3, and I've got 2. So that was factoring by grouping. Can I do that here? Well, let's try it. What's common here? An a. When I factor a out of these two terms, I'm left with c plus d. Now it's plus, right, just like this one was, plus, went right down here. What's common here? A b. I factor b out, and I'm left with c plus d. Ooh, how nice, because it matches. If it matches, I can factor it out of the first term and the second term, leaving me with a plus b. Factoring by grouping. It's so powerful, isn't it? This certainly can be 4 terms. Can a proportion be set up among the 4 coefficients? Factoring quadratics by splitting the middle term. That's what we just did. You multiply the numbers in the first and last terms. All right, so let's say we do that here. We multiply 6 times 35, which is the same as 3 times 70. So that would be 210. And what are the common, what can we do for factors there? We're looking for factors that when we add them together will give us 29. So I could use 21 and 10, but when I add those together I get 31. That's too much. So what else could I do? 110. How else could I factor that? I know it's all going to be positive because I got only positives there, so that's a clue. What do you think I could do? I want to get, what else could I use? Well, how about 730? Oh, well, that's ridiculous. That's already above 29. Can't do that. 7. Stuck on 7. I can't use 7. How about 14? Would 14 go evenly into 210? Would it go? It'll go in once, right? Oh my goodness! Yes, 14 and 15. So we could say 14 and 15. Factor this product until you find the factors that will sum to the middle term. Then factor out the common monomial in the first two. Okay, so what have we got that's common in the first two? Well, an x and a 2, right? So I could factor out 2x, and what would I be left with? I'd be left with 3x plus 7. And then, anything common here? Well, yes, a 5, right? Is there anything else? I think that's it. 5. And what's left? 3x plus 7. And I am ready to squeal with delight because look what I've got. I have a common binomial, and I'm going to factor it out. So I have factored out 3x plus 7, and the factor which is left, 2x plus 5. So here it is, 3x plus 7, 2x plus 5. Factoring by grouping.